Okay, in the last video we just kind of went through an example of a rational function. So let's see if we can't tackle this one. Same scenario. The first thing I want to do is I'm looking for that y-intercept. I'm looking for that y-intercept. So let's just so we set the function equal to 0. If we just plug 0 in, should be able to kind of look at it. Looks like that y-intercept is going to be at x equals 0. So 0, 0 will be that. Let's find out our x-intercept. And that's going to be, well, that's also going to be 0. Okay. So not much going on right there. What about the vertical asymptote? Okay. That's going to happen when the denominator is 0. And notice how no matter what value I choose for x, this denominator is never going to be 0. If I put negative 2 in here, negative 2 squared is 4, plus 4 is 8. 1 squared is 1 plus 4 is 5. On the surface it looks like this thing will always be greater than 4. Yeah, so even if I put like 1/2 in there, I get 4 plus 1/4. So the vertical asymptote does not exist, and that's kind of a breaker, because that's kind of what we that's what makes a rational function easy to graph, is the asymptote. So let's go for the horizontal asymptote though, and see if we get any luck there. Well, it looks like the degree of the numerator is the exact same as the degree of the denominator. So in that case, we use the remember the lead coefficients. Okay, which is just 2 over 1, or just 2. Okay, so we'll just call that y equals 2. So we didn't completely strike out, but we thought things could get a little better than that. So let's just take it down here and draw what we know. So let's just call this 1. Here's 2. So let's just call this our horizontal asymptote. It doesn't have to be perfect. And it looks like we had 0, 0, 0, 0 on our x and y intercepts. And we really don't know much about anything else. Now, one thing we do know is that because there's only one x-intercept, and it's 0, 0. So here's the x-intercept, and there's only one of them. So that tells us that really, in reality, our function is never going to be down here on the graph, and it's never going to be above here. So it's going to be somewhere in here is where it's going to exist. Basically, the range of the function is going to be in here. So let's also think about a couple other things. I think we just got about all the information we can out of that one. So what I'm going to do is I'm going to pick some convenient, easy to graph points, and I'm going to graph them. That'll be f of -1 and f of 1. Okay, so let's go ahead and do that. Let's do f of 1 and -1 and see what we get. Okay, so what do we have? 2x squared over x squared plus 4. So let's see here. F of 1, that's just going to be 1 squared is 1. 2 times 1 is 2. Over 1 squared plus 4 is 5. Okay. F of -1. -1 squared. Well, that's just 1. So that says 2. -1 squared is 1 plus 4 is also 5. And that kind of goes with our logic here, because we decided that the function wasn't going to exist down here in negative territory. So shouldn't really be a surprise that happened, but we wanted to go ahead and check. So 2/5, that's like 40%. So that's not quite halfway, but we'll call it good right there. And here's our intercept right there. And as this thing goes out to as x increases, this thing's just going to go out towards infinity. And it's going to approach this asymptote. Okay, so the graph's going to kind of look something like that. Ooh, I got it a little messed up right there. And just on a side note, Let me do a little side note. I kind of like these side notes. This is just kind of your vision of the future here. 2x squared okay, just kind of looking at this thing right here in this graph. You know, whatever we do to the numerator, we can also do it to the denominator. So watch this little trick I'm going to do. Divide everything by x squared. Okay, and what does this reduce down to? Okay, this goes to 1, this goes to 1. Okay, so I end up with 2 over 1 plus 4 over x squared. Well, as x goes to infinity, you know, x is going out to infinity, as x is getting huge, this is going to approach 0, isn't it? It's going to be almost just, I mean, it's going to be so small it's not even going to be worth mentioning. So we end up with this 2 over 1 business, which, you know, of course is just 2 as x goes to infinity. And see how as x goes to infinity, this graph gets closer and closer to 2? So that's just kind of a little trick, and you'll explore this a little further on in calculus if you go on to take that. But that's just you know, another example right there. So I'm going to do one more, and I think we can call it good on the rational function graphing. All right, thanks.